So we have now defined what cost functions are. We've understood their properties. We've seen them graphically, both the CRS case as well as the cubic cost function case, and we know how to solve cost minimization problems now. Now we're going to understand the factors that could lead to changes in these costs. Now, when we wrote down our cost function, the cost function is always written as a function of V, W, and Q. V and W are the input prices, and Q is the output that is being produced. Now, we mentioned earlier that whenever there's a change, so these cost functions are constructed under the assumption that your input prices are constant, and the technology that we use to produce the output is also held constant. Now, when any of these change, your costs are also going to change. So that's what we're going to study now. So we know that a change in input prices will influence our costs also. But by how much? And how will this change affect us? Well, the increase in costs is going to be influenced by two elements. The first is that how important is this input into the production process? Okay, which makes sense, right? If an input it comprises a large portion of your costs. If it is a really important input, it will take up a large portion of your costs. And if that input becomes expensive, that is going to have a stronger influence on your overall costs. And vice versa, if that input is not that important. So for example, if you're a building contractor, labor is a super important input into your production function. Whereas an input like, say, nails that you will, nails to hang things on the wall, that's not that big of an input, not that important. So if labor prices go up, that's going to substantially affect your inputs. But if your nail prices go up, not so much. Sorry, when labor prices go up, it will substantially affect your costs. Okay, so how important the input is plays a crucial role. The second is that if one of the inputs become more expensive, how substitutable is that input with another input? Now, if a particular input becomes very expensive, but you have other substitutes available to you, then you could swap the costlier input for the cheaper one relatively easily. Whereas if the level of substitutability is not that high, then we're stuck with the more expensive input, and that's going to affect costs in a different manner. So this is primarily how change in input costs will affect our total costs. Now we're going to have a Cobb-Douglas function that we look at as an example, and then we're going to see how this input substitution is happening behind the scenes. So for a traditional Cobb-Douglas production function, we can write down our cost function in the manner that you see in the slide right here. And we actually derived this in an earlier video. So we have our total cost function. And suppose we come up with some numbers for all of these parameters, for alpha and beta. If they're both half, the cost function boils down to a much simpler looking equation. 2q v power half, w power half. Now, if we take some arbitrary values for V and W for the prices of these two inputs, then the cost of producing Q units of output is actually just going to be, you just have to plug in the value of V is equal to 3 and W equals 12 into your cost function, and you get the answer 12Q. So for 12 units of output, it's going to cost you 12Q. And this is a linear cost function. And so AC and MC will just be constants. If we were to change the numbers, suppose labor becomes a lot more expensive. If the price of labor is now 27 instead of 12, if you just plug in these new numbers into your cost function, the cost of producing Q units is actually 18Q. So what happened? Labor actually became expensive by about 125%. Wages went from 12 to 27, an increase of 125%. But what happened to costs? They went from 12Q to 18Q, an increase of roughly 50%. So though the input became expensive by 125%, the actual increase in costs was only 50%. So that's not proportional, right? And the reason here is that when labor became expensive, we substituted that with the cheaper input of capital, And so the actual overall increase in costs is not as much as was projected by just the change in wages. So this is your input substitution that is happening behind the scenes. So we've now seen how costs can change when your input prices are changing. Now we'll see how costs can change when the technology of production changes. So we're again going to use our Cobb-Douglas example to do this. But before we get that, we'll derive the general version of this. So the way technical change gets embodied in cost functions is that when you have better technology, you can produce the same level of output with fewer inputs. So to produce Q0 level of output, you're going to need fewer inputs, which would mean your cost of production is going to go down. So how does this work out? And by how much will your cost functions change? How much will your costs go down? Let's define a production function here. So let's assume that this function follows constant returns to scale. And we have a production function of this form, A of t times f of kl, where A here denotes the innovation quotient, okay? Now, let's assume that at time 0, okay, when at time 0, this innovation quotient is just 1, and it's going to increase over a period of time. In this scenario, let's see what happens in time period 0. At time period 0, if I want to produce Q units of output, well, because the function follows constant returns to scale, the cost of creating the cost of producing Q units of output is just going to be Q times the cost of producing one unit. So this is the scenario in time 0. Now, over a period of time, technical change happens, technology progresses. So when we get to time period t, okay, when you get to time period t, whatever inputs you were using in time period 1, right, time 0, if you use those same inputs in time period t, you're going to be getting more output. So we could think of technological change in two ways, right? You could produce the same output using lesser inputs, or by using the same inputs, you can actually produce more output. So when technical change is happening, whatever input mix gave me 1 unit of output in period 0 is now going to give me more output in time period t. More specifically, it's actually going to give me 80 times, it's going to give me an output that is larger by a factor of 80 in time t. So we're going to write this down in the following manner. So the inputs that I used in time period 0 to produce 1 unit of output, those same inputs in time t will actually give me 80 units of output. Same inputs, more output. That's what this means. Now, if you just focus on the second part of this equation, the cost of producing 80 units of output is nothing but 80 times the cost of producing 1 unit of output. And this, we're anchoring it in time period t. Now, once you write down things in this manner, we could write down the total cost function here. So if I'm interested in producing Q units of output in time period t, so in time period t, if I want to produce Q units of output, it's just going to be Q times the cost of producing 1 unit of output in this same time period t. Now, to get this particular expression, Ct, cost of producing 1 unit in time period t, I'm just going to go to the previous equation. So here we wrote down that the cost of producing, so we had this equation, right? Whatever gave me 1 unit of output in time period 0 is now going to give me 80 units of output in time period t. Okay. Therefore, I can actually write A of t as C0VW1 divided by CTVW1, or I could write CT of VW1 as C0 of VW1 divided by AT. And that just comes from this equation here. So I make that substitution right here. So I have Q into CT of VW1. So in place of this CT of VW1, I just substitute C0 by AT. So you have just C0 by, when you make the substitution, you ultimately end up getting the answer that in time period T, to produce Q units of output, it's going to cost you, the cost of that is actually going to be the cost of producing Q units in time 0 divided by 80. Now let's unpack this. I'm trying to see how my cost of producing Q units will be in a time period T where technical progress is happening. And I see that at time T, to get Q units, that cost is actually going to be how much it would have cost me to make Q units in the beginning of time 0, divided by 80. Now 80 is a number that grows with time. So because 80 is positive, your cost of producing Q units in time T is actually lesser than the cost of producing Q units in time 0. And the costs are actually decreasing over time at the rate of the technical change, which is nothing but 80. So when your technical progress is happening, your costs are actually decreasing over a period of time, and that decrease is commensurate with the rate of technical progress. Let's see an example, and that should hopefully drive home this point. So suppose technical change takes on an exponential form. Suppose technology is progressing at the rate of 3% per year. Innovation is growing at that rate. And we have a Cobb-Douglas. We don't need a Cobb-Douglas function necessarily, but it's just a lot easier for illustrative purposes. So if you have k power half, l power half multiplied by a of t, and suppose your a of t is given by this exponential function. Now, let's go ahead and write down the cost function for Cobb-Douglas functions for this particular case. And we know from the previous slide that the cost in time t of producing Q units of output will be the cost of producing Q in time 0 divided by A of t. So this part is just your cost of producing Q units in time 0. And this part is just your 1 divided by A of t. So this tells you that if input prices stay the same, your costs are actually going to fall at the rate of technical improvement. So this is just so let's see numerically. Now, from earlier, we had these numbers. So I'll just write that down as a recap. So at t equals 0, we had v is equal to 3. And when you said w equal to 12, your cost function actually took the form 12 times q. Okay. So at v is equal to 3 and w equals 12, let's see how your costs are changing from time period 0 to time period 20. Let's see what happens after 20 years. So we're looking at producing Q units of output. We're looking at time 0. And we're looking at time 20. Well, at time 0, we know that the cost is, well, Q. Let's see what happens in 20 years. Assuming we have the same input prices and the same output that we're trying to produce, the cost of producing Q units is actually going to be just 6.6 times Q. So I'm just plugging in V equals 3 and W equals 12 into this equation, and T equals to 20. So my costs have actually gone down. They've actually decreased by nearly 50% because of technical progress. So this video summarizes how your costs can change as a result of when input prices are changing and when there is technical progress. So we just have a couple more sections left in the chapter. So I'll see you in different videos there.